Okay, triple integrals number 7. So, okay, moment of inertia. Now let's remember we have a formula for moment of inertia, right? And here it is, integral r squared delta dv. Right. So I like it, by the way, the way I remember this is r squared dm. It just kind of rolls off the tongue a little bit better, integral r squared dm. And anyway, but this is effectively what it is. So, okay, looking at number 7, we've got the following shape. It's the solid cylinder that looks like this. Right? Okay. This is coming out of the x-axis, like so. And okay, so on this thing, we want to compute triple integral r squared. Let's see, now did it say, yeah, so density is 1, so dm is equal to dv. So r squared dv. Okay, what is r? Is the first question to figure out. And the key point there is you've got to ask yourself, well, what's the axis that I'm rotating around, and what are the points from which I want to compute the distance to that axis? Well, I'm rotating around the x-axis, and I want to compute, if I have some point here, you know, x comma y comma z, I want to know what's the distance over here. What's that perpendicular distance to the x-axis? And I claim that distance, that r, then, is the square root of y squared plus z squared. Now, does that make sense? Is that okay? Is everybody happy with that? So if you want to break that down just a little bit more brute force, the point is that x, y, z, the distance to the axis, this nearest point is going to be x, 0, 0. And so you can just literally compute the Pythagorean distance from there to there, and you get this formula. Okay, right, fine. So we're computing this again, this moment of inertia thing, and it is triple integral. Now r squared, well, that's just going to be y squared plus z squared. Dv, that's dx, dy, dz. Okay. Cool. Okay. So this is just triple integral now. And is that what you were having some trouble with, is the setting it up part? Or
it was actually more so, the setting it up I wanted to see.
Yeah.
Evaluating the triple integral.
Evaluating the triple integral.
Square roots in the domain.
Yeah. Okay, that's okay. So this is going to get a little ugly. But let's see here. Yeah. Okay, sure. No problem. We'll do it. Okay, so let's decide how to slice this. You get to choose the order of the axis, the order of these things. I claim that the dx integral is going to be pretty boring. So just to get it out of the way, I'm going to put the dx on the inside. Note that, look, x goes from 0 to 1, and it doesn't matter what y and z are. So that dx, and there's no x's in here. So I claim that what we're going to get right off the bat is an integral. It's going to be y squared plus z squared. You could think of that y squared plus z squared as factoring out of the dx integral. And the integral from 0 to 1 of 1 dx is just 1, and it's just gone. It goes away. So we have dy dz. And y and z relate by the cylinder. So let's look at this. That's sort of the relationship between y and z there. So y squared plus z squared less than or equal to 1. So z goes from 0 to 1, and then y goes from negative square root of 1 minus z squared to positive square root of 1 minus z squared. Is that okay? Alrighty. Okay, moving along. So the y antiderivative, yeah, so there's cubes in here. It's annoying. We've got 1/3 y cubed plus yz squared, where y goes from negative square root to positive square root, etc. So I get integral from 0 to 1. Okay. By the way, this is an odd function of y, right? Because that's an odd power of y, that's an odd power of y. So when I plug in this one and when I plug in that one, this term is going to be the exact negative of that term. So when I take that term and subtract that term, I'm just going to get 2 times this one. So let me just put a 2 out here, and I'm just going to plug in just this term. Does that make sense?
Yeah.
Okay. It's a little algebraic fast one. Be real careful when you do little algebraic fast ones like that, because it's easy to oops it and then get a wrong answer. Okay. Okay. So 1/3. Now I'm going to have this square root cubed, which I claim means we're going to have 1 minus z squared times square root of 1 minus z squared, and then plus y. Let's see. So then, well, we've got z squared times square root of 1 minus z squared dz. So I claim we've got this, and this will simplify a little bit. I've got 1/3 times this square root. Then I've got, let's see, I've got a 1/3 z squared times that square root. And then here I've got a z squared times that square root. So altogether, I've got 1/3 times the square root. And then plus 2/3 times z squared times that square root. Is that cool? I just collected, so there's a z squared times this square root term there, and there's a z squared times the square root term there. I just combined them together. This is minus 1/3,
Okay, so
that's plus 1.
in the last line there, the left-hand term is gone now, right?
Yeah, the term that corresponded to that has been combined with this.
Oh, never. Okay.
Yeah.
Okay.
Is that cool? Is everybody good? Okay. All right. This is from 0 to 1. So at this point, we've got a couple of Math 32 problems, and this is the kind of thing that's it's going to come up. It's unavoidable. It's just kind of the way it is. I've got some really good news for you about this one. That's not going to be that bad. Oh, but let me rewrite this a little bit. 2/3 integral 0 to 1 square root of 1 minus z squared dz. And then here we've got 4/3 integral 0 to 1 z squared square root of 1 minus z squared dz. Okay. This integral here is one of my favorite integrals in the world. It's awesome. It's so easy, you're not going to believe it. So here it is. I played it up enough. Let's look at how would I interpret this integral geometrically. Well, I claim that this integral, geometrically I would interpret this as computing the area under, well, I'd be looking at, some y equals this function of z, and maybe call that the z-axis, and y, the thing that I'm integrating, is square root of 1 minus z squared, which means that y squared plus z squared is 1, which means we're talking about a quarter circle, and we're integrating from 0 to 1, which means it's 1/4 pi. Isn't that cool? We evaluated an integral with geometry, right? Usually we use integrals to help us compute areas. Here we used an area to compute an integral. Like I say, that's one of my favorite. I think it's super cool. So that is pi over 4. Okay, now what about this other integral? What about this guy? I claim that you can use an integration by parts. Now you could do a trig substitution because, by the way, whenever you see square root of 1 minus something squared, trig substitution is very often the right answer. It's a trick on this particular problem. If you integrate by parts with u equal to z and v prime equal to z square root of 1 minus z squared, I claim this works out really nicely because this you can find an antiderivative of with just a regular substitution. I mean, you've got to do a substitution to figure out what that antiderivative is, but it works. Just let, g equals 1 minus z squared. Then dg is going to have that z in it, and so you can work that out. Of course, u prime is just 1, and so you can turn this integral by doing an integration by parts into something that actually looks a lot like this, just different constants. So that's the trick on that side. Does that make sense?
You see the last one?
Yeah. I claim if you use integration by parts like so, you can make this integral turn into, integration by parts turn the integrals into different integrals. And I claim what this turns into when you do the integration by parts is a lot like this. And you figure it out by the same technique.
Okay.
Yeah. So, and of course, don't forget these constants, the 2/3 and the 4/3. Right.
And what would a trig substitution look like?
Trig substitutions are where you take stuff like if you have an integral of, let's say, like z cubed square root of 1 minus z squared. It's this trick where you say, well, I can make this simplify pretty nicely by just, if I were to just choose to let z equal to sine theta, then note that dz is cosine theta d theta. But more to the point, square root of 1 minus z squared becomes just cosine theta.
Okay.
And so you can turn an integral where you're like, I don't know, what in the world am I supposed to do with this, into a trig integral where you can use trig identities and knowledge of derivatives of trig functions, etc., and you can actually deal with a lot of stuff that looks like this. So that's kind of the first guess that you might make when you find yourself faced with this integral. It looks like a trig substitution because of that expression there. But this particular case, it happens to be, again, you can break it down with integration by parts.
Thanks.
Yep. Okay. Is everybody good? Yeah, question.
How does it work?
How does this work?
Yeah.
Yeah. So integration by parts, you take the integral in question, and you've got to figure out how to interpret the integrand as a...
What the particular one.
Yeah, so the point is you break this down as a product like so, and which is weird because normally you would break up the z squared and then the radical. Here you sort of split the z squared in half, do it like this. And I claim that anti-differentiating z times the square root of 1 minus z squared, it's just going to be to the the 3 halves.
Yes.
Yeah, that's right. Yep, which you can deduce with a substitution. Let g equal to 1 minus z squared, then this is part of the dg. The little z there is part of the dg. So you can do this antiderivative here with a substitution.
Yeah, and you get v equals 1 minus z squared to the 2/3, right?
To the 3 halves. And then there's going to be there's some constant out front that I can't quite do in my head. Probably 2/3.
And you're going to have to integrate v again, right?
Yeah, that's right. And
So it's going to be another...
wait, hang on a second. Oh, hang on a second. Did I do this wrong?
Thanks.
Oh, I'm sorry.
It should work if the square root part was in the quotient.
Oh yeah. Okay, I lied. I'm sorry. You got me. That's okay. I was wrong about. Yeah, no, you're right. This doesn't work the way I thought it did. I thought this was going to work out. No, yeah. What's the matter with me? Yeah. It turns it back into something else that you'd still want to do a trig substitution with. So let me just cancel this and say, yeah, just do this with a trig substitution. Yeah, I remembered that worked out, but I guess I remembered wrong.
If the square root part wasn't at the bottom.
Yeah, that's right. It would be more convenient if that was in the bottom. Yeah, that's right. Yeah. Okay, anyway, but certainly you can do this with a trig. So just ignore all of this here. You can certainly do this with a trig substitution. Yeah, right. Okay.